Welcome to lecture 20 of our CT6 CS2 classes. And today we'll continue with where we left off in the last class for time series. So we discussed that, there are certain kind of models that we have. So we have to remember that what we are looking at is a linear time series, and which is why the models that we have are going to be for the linear kind of a model. So the first model that we looked at was autoregressive model, and wherein we knew that just by its name itself, we know that it's autoregressive. So regression upon itself, which is why we see that we have xt here and xt minus 1, xt minus 2, up until xt minus p. And this p determines the order of the autoregressive process that we're looking at. So we know that this xt depends on xt minus 1, t minus 2, and its own lagged values basically. And the second kind of model that we had, just, so we only did this introduction for these models. We'll look at in detail today all of these models. So when we talk about the MAQ model, the MA means moving average model. And there you will see that, this xt depends on today's error term and its lagged values as well. And this ARMA is just a combination of AR and MA, where this xt depends not only on its lags, but also on its errors lags. And today we'll have a look at what's the connection between AR and MA. If you have an ARP process, can you transform it into some MA process? Or if you have an MA process, can you transform it into some AR process? And if it's even possible or not. So the technique or the tool that which we are going to heavily use to perform these actions and to study these models in detail will be this. So backward shift operator. And we know that if I apply this backward shift operator to my xt, what I get is xt minus 1. And if I apply that twice, what I get is xt minus 2, and so on. And we studied something called as difference operator as well, which is just 1 minus the backward shift operator. So let us start with the AR model, and just to have a glimpse of the AR model, let us let us not generalize it at first, and we'll try to have a look at the AR1 model initially. So let's say that we're going to study AR1 model. So if I were to write my AR1 model, so let me just go back to where I wrote the models. What will I have is this term, and not this term, because I'm saying that my order is only 1. So I'll only stop here, and I'll have this error term as well. So I'll just write my AR1 model, and it is just xt right. So we know that this is how we can define an AR1 model. But let us see if there's another way of writing this model just in E terms. So what I can do is I can substitute this xt's expression at t minus 1 instead of this xt minus 1. So what I will do is I will just rewrite this equation as mu plus alpha, and now instead of xt, what I will do is I will rewrite the whole expression of this with t as t minus 1. So mu will still be mu plus alpha xt minus 2 minus mu is again just a constant. So plus e t minus 1. Because my t is t minus 1 now, so I'll have a look at t minus 1 here. And that was my xt minus 1. But then I also have minus of mu, and bracket will complete, and plus et. Does everyone understand what I did here?
Yes.
Okay, thank you. So please let me know if you do not understand any of this step. Okay. So next what we will do is, we can see that I have alpha times all of this bracket. And I can also see that I have this plus mu here and a minus mu there. So I can just cancel both of them. So this will just be alpha squared xt minus 2 minus mu, right? Plus alpha times et minus 1 plus et. So, okay, we just have now an expression of xt with xt minus 2. So we don't have xt minus 1 anymore. So we see that there is still some coefficient to xt minus 2. So we know that xt is dependent on xt minus 2 as well. Okay, but see, we started off with, saying that xt just depends on xt minus 1. But we also know that xt minus 1 depends on xt minus 2, which is why even xt depends invariably on xt minus 2 as well. So let us maybe try to, if we try to expand this even more, we'll see that this will just become mu plus alpha cube xt minus 3 minus mu plus alpha square et minus 2 plus alpha et minus 1 plus et. And I guess there's some, yeah, so that will be it. And if you just go on expanding this on and on, at the end, so here you have t minus 3, right? And you expand it, you do the same process t times. So what you will get is mu plus alpha raised to, instead of 3, you will have t. And here x t minus t, which is nothing but just x0. So x0 minus mu plus. And here you will have a sum of all of these ETs. So you start with ET minus J, where your J will start from 0 and go on till T minus 1, right? So because here we had alpha raised to 3, you see for the E coefficients, we only had up until 2, right? So here we have T, so here we will only have till T minus 1. And now we also have to take into consideration that we not only have E, we have this coefficients alpha squared as well. So again, here I'll have alpha raised to J. So here J was 0 and alpha raised to 0 is just 1. And over here J is 2, so alpha raised to 2. So alpha raised to J, T minus J. So we know that I can write my XT process in terms of this series of E process, right? And remember, what I'm looking at for now is a AR1 process, right? And let us say this is it, like I have rewritten my model, and now I know that I want my model to be a stationary model, right? Because then and then only I can perform some operations. So can someone remind me of what are the conditions that we require for a process to be stationary? Anyone? What is the first condition?
The mean variance should be constant.
Yeah, the mean and the variance should be constant. Okay, so let us try to devise the mean for this process. So now we are looking at how we can make this process a stationary process. Or rather, when is this process a stationary process? So let us calculate its mean. So we all remember, we always assume that all of these E's that we have are IID, normal, 0, 1. So for mean, this will just vanish away, right? Because expectation E is just going to be 0. So if I were to rewrite expectation of XT, it will just be expectation of mu, which is mu itself because it is a constant, right? And then I have plus alpha raised to t, expectation of this thing, which will be expectation of x0 minus mu, right? And I know that the mean of all of these summations would be 0 because these E's are IID and their mean is also 0. Does everyone agree with that?
Yes.
Okay. So now let us define my e raised to xt as mu subscript t. So it will just be equal to mu plus alpha raised to t. So now I have subscript as 0. So this will be mu 0 minus mu, right? Okay. But my condition for stationarity is that my mean of the process should be a constant number. It should not be dependent on t in any ways. So we want that this term should go away so that I am only left with mu t is equals to mu, right? So we also know that it should be the same, and it should not only be a constant number, but it should also be constant across time. So we know that even for mu 0, it has to equal to mu. And we can easily see that if my mu 0 is equal to mu, then this term becomes 0. And there is no effect of this t here. And my mu t will also be mu, which is just a constant, right? So we devise that the very first condition that we require for this process to be stationarity is that mu 0 should be equal to mu.
Also, alpha could be equal to 0.
Hello.
Hello.
Yeah, did you say something?
Ma'am, also alpha could be equal to 0.
Also, alpha could be equal to 0, yeah. So if my alpha is equal to 0, yeah. So if your alpha is 0, you know what will be your mu t? It will again be mu, right?
Yes.
So if my mu t is mu, then all of my mu, so my mu, irrespective of whatever t is mu, right?
Yes.
So even if it's 0 or t, it's always going to take the value mu. And the next condition that we have is that alpha can be 0. Okay, let's keep that in mind. So either alpha can be 0, but this condition has to hold, irrespective of if alpha is 0 or not, right? Because even if alpha is 0, we will have the conclusion that my mu at time t is just mu. All right. Good. So next we have something about variance. Let us try and figure out the variance. Maybe I should. Yeah. So if I were to write the variance of this process, I can rewrite it as variance of xt. Okay, so that will just be variance of mu plus. So I have alpha raised to t here and x0 minus mu. So it will be, this coefficient will come out as squared and it will be variance of the remaining term. So I can write this as alpha raised to 2t variance of x0 minus mu, right? And then the variance of those summations. Right? Okay. So let's try to see what the variance is. And what will be the variance of a constant?
0.
Perfect. And here what can I have? What will be the variance of x0 minus mu? So my mu is just a constant, right? So I can again maybe expand it, but there shouldn't be any need of even the expansion because you should
Variance
already
of
know
x.
this by intuition. Yeah, that it will just be variance of x0, right? The covariance term is going to be 0 and the variance term for mu is also going to be 0. So you will only be left with variance of x0. But intuitively also you know that even if you subtract any constant number or if you add any constant number, the variance will be the same. Okay, so now next up we have variance of these guys. And let us take this summation outside and the variance inside. So we have summation j going from 0 to t minus 1 and alpha raised to j is just constant. So it will come out with a square and I'll be left with variance of P minus J. Okay, so when I said here that we are looking at IID normal 0, 1, let us for now not consider as 1, but that is generally the case. But for AR process, let us first try to look at if we have some sigma square. So the variance is sigma square, but not 1. So now we have alpha raised to 2t variance of x0 plus. So I know that this is just sigma square. So I'll have summation j going from 0 to t minus 1 alpha raised to 2j sigma square, right? And sigma square is nothing but a constant. So you know the value that sigma takes, or even though you don't know, it can just be a known constant. So this, in effect, boils down to the calculation of this term and doesn't even know how to figure out what will be the value for this term. What am I doing here? So let's say sigma is just a constant, right? I take sigma square outside because this is independent of j here. So I'm left with only this term here. So if I, let's say, try to expand this here, what do I get? I get something like alpha raised to 2 times 0 plus alpha raised to 2 times 1 plus alpha raised to 2 times 2 and so on. And this is nothing but 1. So this is a sum until alpha raised to 2 times p minus 1. So the number of terms that you have are t because you start from 0 and not 1. So using the GP formula, the geometric progression formula, what you will get is the sum of this series till t minus 1 starting at 0 will just be 1 minus alpha raised to 2t upon 1 minus alpha square. So you see the r here is nothing but alpha square because alpha raised to 4 upon alpha raised to 2 is just alpha raised to 2. So I hope everyone knows the formula that I'm using there, right? So this is just, let's say if you have u plus ur square up until ur and minus 1. This is equal to u times 1 minus r raised to n upon 1 minus r. So here n is the number of terms you have and r is the thing that gets multiplied each and every time you progress. And u is the first term that you have. So sometimes this is also called a and you write AR. So it's just a matter of notation, nothing changes. Okay, so yeah, I hope that's clear. So next up, if I were to write again, this will just be variance of x0 plus sigma square. And now I just have to rewrite this, which I know is that. So 1 minus alpha is to 2t upon 1 minus alpha square. Does everyone agree with this?
Yes, ma'am.
Good. So the another condition that we had for a process to be stationary is that its variance should also be constant, right? It shouldn't be dependent on t. So what can we do here for the variance to be constant? So let us see what all terms we have. First of all, we have this alpha raised to 2t again. So again, this depends on t. And then we have something sigma square. And the denominator doesn't depend on t, but this numerator does depend on t. Sorry. So we again have alpha raised to yeah. So we again have alpha raised to 2t here, right? And if I were to say that I want my variance to just be a constant for my AR process to be a stationary process, maybe if I look at this term separately, what I can do is instead of writing this as a whole bracket, I can separate this numerator and rewrite it again as minus alpha raised to 2t sigma square upon 1 minus alpha square, right? So this is my another term that I have. Does this make sense? I've just separated them, and because we have sigma square outside the bracket. So now if I see, if somehow by magic, I can vanish this term and that term, because this term is independent of t. So if I can just write my variance as this thing, it would be a constant. So sigma square and alpha square, these are just constants, right? So can I do that? Or what should the case be so that I end up with my variance as just this, guys? Can anyone guess?
Alpha equals to 0.
Alpha equals to 0. So let us see what happens if I have alpha equals to 0. If I have alpha equals to 0, this becomes 0. So even before doing all of this, let us see what happens if alpha equals to 0. So for AR1, I have this process, or rather I have this process, right? And if my alpha is 0 here, what I am left with is just xt is some constant plus the error term, which is nothing but just a white noise process, right? So I'm not even modeling anything if I just say that my alpha is 0, right? The very essence that we're trying to capture, the very dependency for which we're trying to use this model vanishes if I put alpha equal to 0. Can you see that? So we know that alpha equal to 0 should never be the case. Alpha should take some value, but not 0. And there is another reason why alpha shouldn't be 0. So this is actually the main reason. But we'll again see what happens if alpha takes the value 0. Oh no, sorry. That's the only reason for why alpha cannot be 0. So now even alpha cannot be 0. So what else can you do? Anyone?
If you can take variance of x0 equals to sigma square 1 by 1 minus alpha square.
Yeah, so we know that if I have my variance of xt as only this term which is in the middle, so sigma square upon 1 minus alpha square. So I know that this should ideally be my variance of xt, right? But I can never have these terms along in the variance. So remember the time when I discussed with you guys the AA infinite series? So this is what will come into picture now. So what I will do is I will take this term on the left hand side and I'll write this expression that I have here as variance of xt minus sigma square upon 1 minus alpha square is just equal to, so I can take alpha raised to 2t common. I'll take alpha raised to 2t here, and variance of x0 minus sigma square upon 1 minus alpha square. So this looks something like the expression that we had for mean as well, right? We had some here, alpha raised to some coefficient of t, and then expectation of x0 minus mu, and again expectation of xt, which is equal to mu right there. So again, we have something similar. So the variance of xt should be equal to this. So we know that this side should be equal to 0, but it is actually never 0 until and unless you look at the time when t goes to infinite. So if you consider that t goes to infinite, and also the fact that this alpha takes the value less than 1. So my mod of alpha is less than 1. Then those will be the cases where if you increase the t, this coefficient is going to decrease, right? Because if I'm raising a number which is less than 1 by a higher and higher value, it is going to take a lower and lower value, right? So I know that virtually at some point of time, my model is going to become a stationary model. So we say that in the long run, that is when t is tending to infinity, my variance is just equal to this thing right there. So this is also important for us. Okay. And the next thing we know is, again, if I want this variance to be a valid variance, I know that this should not be infinite, and it will be infinite if my denominator is 0, which will be the case if alpha is 1 or minus 1. So I know that this should never be the case, right? And I also want my variance to be a positive number. So let's say my variance of xt should be greater than 0 always, right? So I have sigma square upon 1 minus alpha square to be greater than 0, which implies the sigma square is always going to be greater than 0. So we only want this denominator term to be greater than 0 and not be negative. So I know that my 1 minus alpha square should be greater than 0. So if I just take it that side, I'll have alpha square should be less than 1. And which just translates to the fact that my mod of alpha should always be less than 1. So you can also not do all of this process, but just directly claim that this number that you're subtracting from 1 should be lesser than 1. So any number that you are squaring has to be lesser than 1 in absolute terms. So it can be minus 0.8, but it cannot be minus 1 or minus 2. Is that clear to everyone? Does this make sense?
Yes.
Okay, so let us do a recap of what we just did. We started off with the AR1 process. So remember, we are still looking at autoregressive process with the order 1. And we did some recursive substitution, and we got another expression for the same AR1 process, xt. And now we're trying to figure out in what conditions this xt process is going to be a stationary process. So we got the first thing that, so the very first thing that we have to consider is that my mean should always be mu. It cannot be anything other than mu. And it should be a constant. And that is how we derived that particular value, right? And the next thing that I have is that my variance should be this guy. So my variance is this. And the next important thing is that my alpha, so the absolute value of my alpha is always less than 1. And these are the three main conditions that you need for this AR1 process to be a stationary process. So remember, we are still looking at an AR1 process only. And we'll have a look at what happens if you increase the order of the AR process. But let's just have a look at the covariance of this process as well. And again, before we dive into the covariance, let us rewrite this model again in using the double-sided infinity process. So what I will do in essence is okay. So remember what I have here. What I have here is, let me just copy that. Yeah, so we started off with something like this, and now I'm saying that I'm not only looking for time from 0 till infinity, rather I'm looking at time. So I have my xt where my t takes values from minus infinity to infinity. And that is what I say when I'm looking at, a double-sided infinite process. So if let's say I'm using that kind of a process, I should never stop at 0 here. I can still go on and on, right? Recursively substitute it again and again till I get something like this. So I'll just keep doing this forever. So I'll again substitute x0 in here and I'll have some minus terms and I'll never stop at t minus 1 here. I will increase this. So I will again add plus 1. So it will become t. Then it will become t plus 1, t plus 2, t plus 3, so on till infinity. Because there is really no stopping to this process now. So I have this going on till infinity and alpha raised to j e t minus j as the subscript. So this is how you rewrite AR1 process as a double-sided infinite process. Does this make sense to everyone? So again, now if you try to figure out its expectation, so let us carry out the expectation of xt. It will just be mu, right? Because all of these expectations are going to be 0. And if you write the variance of xt again, so the variance of constant term will be 0. And what you will be left with is summation j going from 0 to infinity, alpha raised to 2j, variance of et minus j. And this is nothing but sigma square, right? Does this make sense?
Yes, ma'am.
Okay, and also remember, the term that we used was covariance, right? And here, if I'm writing my variance of xt, it is nothing but just a covariance with itself, right? So this is a this is a autocovariance with lag 0. So I can rewrite this expression which I have here with sigma square as gamma 0. Does that make sense? Okay, so this is about the covariance with lag 0. Let us now try to see what happens if I increase my value of lags. So Let us say I have now a lag of k. So what I will have here is gamma k. So I'll have gamma k, right? Which is nothing but just covariance between xt and xt plus k. So k here, that's the difference that we're looking at. So again, now my xt can be written as this. And if I'm writing my xt plus k, okay, let me just write it down for the first time. So for my xt, I will rewrite this constant and all of this thing. So I know that when I'm talking about my variance, this constant really does not matter. So I'll ignore that constant and I'll just write this term which really matters. So summation j goes from 0 to infinity, and I have alpha raised to j e t minus j. So this is my xt. And now I have to write xt plus k. So I'm just going to write summation I going from 0 to infinity. Sorry, there should be 2j. Alpha raised to 2i. So this is alpha raised to I, t of. So now instead of t here, I would have t plus k. So this will be t plus k minus I, right? Does this make sense? So what I did was, I just substituted t plus k instead of t in whole equation, and I didn't write these new terms because this don't really matter when I'm talking about the covariance. So now again, I know that my e's, these are independent variables. So E1 and E2. So let's see if I'm talking about the covariance of E1 and E2. It is going to be 0. So covariance of EI, EJ is equal to sigma square only if I is equals to J, right? Otherwise not. So we know that these subscripts have to be equal to each other for this covariance to not take the value 0. And we don't care about 0 anyways because we're just adding all of these terms and it won't add anything substantial which will change the answer. So we ignore all of these terms which will have the covariance of this, comma this as 0. So we have some terms in here and we have some addition of some terms in here, but only those terms will matter wherein the subscripts are same, right? So I'll rewrite this condition as where my t minus j is equal to t plus k minus I, and then this t and t will get cancelled and I can take this there and that there and I will get my I as j plus k. So now I have that only when my I is equal to j plus k, I will have something other than 0 for this value of covariances that I'm looking at. Okay, so let us now simplify this. And this looks a monster right now, but just by this simplification, it will become something like, so we have alpha j here and alpha I there, right? So I'll write alpha j. Maybe I can take that outside. So let us try to do something else. Okay, maybe I can do that in the next step. So we have covariance of, no, you cannot do that in the next step. Okay, so if I'm looking at my covariance of this guy and that guy, I'll take this coefficient outside of the bracket. So I'll have alpha raised to g, alpha raised to I, right? And the summation will still be there. So I'll have summation going from g and summation for I, right? And I'll be left with covariance of Et minus j, comma, Et plus k minus I, which will be nothing but just sigma square for when this is equal to that. So now I will just substitute instead of I, j plus k. So I have alpha raised to j and alpha raised to, so instead of I, I'm writing it as j plus k. All right. And I again have the summations as it is. So now when I'm, not talking about this I can ignore this. And what I will have is just the summation of j going from 0 to infinity and this term, which is going to take the value sigma square. So now if I try to combine this, so I have alpha raised to j and alpha raised to j plus k. This will be what? This can just be okay, so there is one issue. What we did was, we took this alpha raised to j outside of the summation, where this still depends on the j that we have. So we cannot do that. And instead, what we will do is, we will write these summations outside. So we have to write the summations for j and for I outside, and alpha raised to j and alpha raised to I inside. And we again have our covariances there. Did you understand the mistake that I made? So my alpha still depends on j, and I took it outside the summation, which I shouldn't have, because the summation is across the value j. So I cannot really do that. And now I have this expression, and what I'm left with is, so again the summation will be outside and not inside. So I'll have summation j going from 0 to infinity, this thing, and so this is just alpha raised to j, and instead of I have written j plus k, and now I have covariance of this thing, which is going to just be sigma square, because I'm assuming that I is equals to j plus k. And for all the other things, for all the other combinations of I, j and k, this value will just be 0. So it wouldn't matter anyways. All right. So now we have this value, and we have alpha raised to j times alpha raised to j plus k. So I can again rewrite this as summation j going from 0 to infinity alpha raised to 2j plus k sigma square, right? So I'll just continue this here. What I have is summation j going from 0 till infinity alpha raised to 2j plus k. So now instead of writing it as plus k, what I'm going to do is just write this as alpha raised to k times sigma square. And now I know that my summation is only over j. So this is indeed a constant, and I can rewrite this whole expression as alpha raised to k summation j going from 0 till infinity alpha raised to 2j sigma square. All right. Okay. So now if I have a look at my variance of xt, what is it? It is just summation j going from 0 till infinity alpha raised to 2j times sigma square, which is exactly what I have here, right? So I will replace this as alpha raised to k, and this whole thing can just be gamma 0. Does this make sense?
Yes, ma'am.
So what we have at the end is that my gamma k is equal to alpha k times gamma 0, right? That is the conclusion that I have now. And so again, if you see, let us go on the next page. So now if you see, we have just derived the autocovariance for the lagged value of k using this expression, right? And is there another way of doing that? So let us see if there is another way of doing that. You know, if you do not expand the whole AR1 process, you can also do so another method which will help you to figure out the autocorrelation as well very easily. So let us see what we can do. So if I'm looking at autocovariance at lag k, I can rewrite this as covariance of xt comma x t minus k, right? Because we know that this is an even function and it is equal. Okay, and I will just substitute my xt here. So I have it as mu plus alpha xt minus 1 minus mu plus et comma x t minus k. Okay, so now as you look at this is a constant. So covariance of any variable with a constant is going to be 0. This is an IID random variable. That's also going to give us a covariance of 0. This is a constant. So the term that matters is just this term, and this is alpha, and the coefficient over there is 1. So we'll have alpha times covariance of xt minus 1 comma xt minus k. And now, if I were to write this as autocovariance, what should be the subscript here? Anyone?
K minus 1.
K minus 1, right? So it's just t minus k minus t minus 1. And you can have the absolute value and it wouldn't matter. So now I have a expression which says that my gamma k is just alpha times gamma k minus 1. So I can again substitute this gamma k minus 1 as alpha times gamma k minus 2, right? So I just use the equation again for alpha k minus 1 to rewrite it as alpha times k minus 2. And I can again do this recursive substitutions over and over again till I get alpha raised to k gamma 0 for my gamma k. So the thing which took us so many steps and so much of a mess to figure out can actually be figured out very easily if you use this kind of a process, right? So what you have to do is you keep the variable that you have on the RHS as it is, and you expand the variable that you have on the left hand side, and then you try to figure out all the combinations and you devise, and instead what you get is a recursive expression, and at the end you get whatever you are willing to derive. So now we have this gamma k. So this is the autocovariance. And the next thing that we care about, okay, so we also have to keep in mind that this covariances should be independent of t, which they are. So we only have alpha square, not t here. And these are in essence independent of t, right? Because we have gamma 0, which ultimately determines any gamma k. And gamma 0 is nothing but the variance. And we made sure that our variance does not depend on t. And it is just sigma square upon 1 minus alpha square, right? So these covariances are also independent of t, and thus they only depend on the lag that you're looking at, which is k. Good. So let us now have a look at the autocorrelation. So how do we define autocorrelation? What is the formula for autocorrelation? Does anyone remember?
Gamma K by gamma naught.
Yeah, so I denote it by rho K, and that will be gamma K upon gamma naught, right? So if I'm looking here, I can just take this gamma naught there, and what I will get is, for this AR1 process, gamma K upon gamma 0 is equal to alpha raised to K, right? So that is true for all the values of K that we are looking at. So this is the autocorrelation. And the another thing that we studied was partial autocorrelation. So we look at the partial. So I denote my autocorrelation function as ACF, and I can just write partial ACF, which henceforth I'll be just writing PACF, and this I denote by phi, and this is denoted by rho. So if I were to write my phi for lag 1, what will that be? So you don't have to remember how you derive this partial autocorrelation functions. If you just open your table booklet and if you look at the page number 40, you will see that there are formulas given for partial autocorrelation function. So what we have is, for phi 1, it is just equal to rho 1. And what is my rho 1 here? So so this is my rho K, right? So if I were to figure out my rho 1, K is just 1, which will be just alpha, right? And if I have to figure out phi 2, so if you look at the page number 40 again, they have this formula as rho 2 minus rho 1 square upon 1 minus rho 1 square. And if you use that, we know that rho 2 in this case will be alpha square, and rho 1 is just alpha, and its square is again alpha square upon 1 minus alpha square, which is just 0. So does this make sense to you guys? I think the very first question that comes to my mind, at least when I see this, is, okay, I'm looking at partial ECF and I'm looking at ACF, but I'm deriving my partial ACFs using the ACFs. So if I know my rho 1, I can know my phi 1. And if I know rho 2 and rho 1, I can figure out my phi 2. So what this partial ACF in essence does is just rearrange the ACFs in a way which gives you the meaning. So remember, when we try to look at what PACF means, what we did was we took the minimum of the error squared to fit best. So maybe I can look back to this. So we took this minimum, right? And we know that for lag 1, it is just the coefficient of my xt minus 1. And for lag 2, it is just the coefficient of xt minus 2, right? So that is one intuitive explanation that is given to us by the partial autocorrelation functions. But you know that the calculations are very difficult and you only have to look at these two. I mean, if at all it comes up in the exam, they can only ask you either the first one or the second one. They will never go beyond 2, because in real time, you will have the computers with you, which will give you the graph of PACF, and you won't even have to, figure out these expressions. But you have to know this just in case. So for exam purposes, ACF will be the thing which is of much more importance than the PACF. And we'll have a look at, how ACF and PACF helps us to determine what kind of a model should we look at. So what happens is, let's say if you're working with some time series, let's say you have pollution levels in Delhi as a time series across the time periods, and you have the values for each and every year, let's say. So what you will do is you will put it in the R and you will just use the function ACF, and that will give you the ACF plot of the pollution levels, and you will use the function PACF and it will give you the plot of the PACF. And using those plots and using and seeing where it declines and where it cuts off, which I'll discuss later in the class, you can determine what kind of a linear model should be fitted to the pollution data, if at all you're trying to fit a linear model. So I hope that's clear to everyone.
Ma'am,
Yes.
ma'am, we found phi 2 only using the formula.
Yeah.
Okay.
So the formula is on the page number 40 of your table booklet. Okay. So this is all about AR1. And now you want to maybe try. So this is just the AR1 process, which is a very special case. And now we'll try to generalize this whole thing for an ARP process. And we will see what conditions should be satisfied if you want the ARP process to be a stationary process. So now we are looking at AR process with the order P. Okay, so if I were to write the model, what I will have is xt as mu plus. So remember, previously we only looked at the one lag, so we only had one alpha, but now we're looking at p lags, so we'll have p alphas. So this is alpha 1, alpha 2 till alpha p x t minus p minus mu plus error term. Okay, so now is the time where we will put to use the tool that we studied of backwards shift operator. So what I will do is, I will have xt here and I will shift all of these lagged xt terms from here to, so I'm shifting them from right hand side to the left hand side. So what I will have is minus here, instead of plus again minus, and instead of plus again minus. And this will be equal to just mu and et, right? Okay, so what I can do again now is use my backwards shift operator. So I know that if I use b on any constant, it will just give me the constant again. And if I use it on xt, it will give me xt minus 1. So what I do is, I write xt minus u here, and I'll have some terms in the bracket here. So I'll do 1. So now if I have 1 here, what I'm looking at is xt and this mu here. So this corresponds to the one that maybe I should highlight this. So this one here corresponds to xt and this mu over there. So xt minus mu, right? 1 times xt minus mu gives you this xt minus that mu if you shift it on the LHS. So the next term is this. I have alpha 1 times xt minus mu minus mu. So I'll write my minus there. So I have my minus there and I'll write alpha 1. And now remember what I have in multiplication here is xt minus mu. But what I want here is xt minus 1 minus mu. So I'll write a b here. So that if I multiply this down with so this is corresponding to this here, right? Does that make sense?
Yes, ma'am, right.
Everyone? This is very important. Did you understand what I wrote over here? So what I did was, I have alpha 1 b times xt minus mu, right? I know that if I can rewrite alpha 1 as just alpha 1 there, and b of xt will be what? Xt minus 1, and b of u will be u. So I get what I want using this function, right? And I'll do the same thing for every other process. So here I'll have b square y because I want x t minus 2 here. So I'll have b square, and that will go on up until b raised to t. Does that make sense? So what should I have now on the right hand side? What will this be equal to? Anyone?
ET.
ET, right? Because I have already taken my mu into consideration. So my mu, xt minus mu is already done with, and I'm left with only ET. So I'll only have ET there. Okay, so now this is the ARP model written in terms of backwards shift operator, right? And now I'm just going to say a couple of things, and you take it for granted for 5 minutes, and you will see when I give an example, how does it play out, okay? So what I do is, I will substitute, instead of this b here, I will write it as some z. So my z is some another random variable. So I'm taking this expression and I call it the, and what I do is, instead of b, I substitute it as z. So what I will get is something like 1 minus alpha 1 z minus alpha 2 z square till alpha p z raised to p. So this is what I have. And I call this equation that I have here as characteristic equation. So it is not yet an equation. I don't have equal to signs here, right? So this is just a characteristic polynomial. Of my ARP process. So yeah. And now what you do is, you try to figure out the roots of this polynomial. Remember, we used to have this quadratic expression and you figure out the roots of this quadratic expression. And that is the same thing that you're going to do here. Instead of the quadratic, now you have p times. So this polynomial is a p order polynomial instead of a second order polynomial. So to figure out its roots, what you do is, you will equate this polynomial to 0. This is what you do, right? Always if you want to figure out the roots. Let us say you look at the simple example, x squared plus 5x plus 6. You want to figure out what are the roots. You equate it to 0 and you use either the minus b plus or minus formula, or you factorize it and you will get something like this for this particular case here. So this is the kind of same thing that you're doing here. Instead of just curving it here, what you're doing is you're allowing it to expand till p. So I erase this. So now I don't need that. So what I do is I figure out the roots, and because I have z raised to p, I will have at most p roots. So if I have a quadratic expression, I know that if I figure out its roots, I'm at max I can get 2 roots, or sometimes 1 root if they are of the same values. So here I will have p number of roots, and I will call those roots as z1, z2 till zp. And these can be equal to each other as well and may not be equal. And the condition that is required now for an ARP process to be a stationary process will be that all of these roots in magnitude take a value which is higher than 1. So the mod of these values should be greater than 1. All of these values. And we'll have a look at why is that the case soon. So let us start from the beginning now. So now I will assume that my process is a stationary process, and we'll try to have a look at, why do we need these roots to take a value which is greater than 0, which is greater than 1. So let us start with a case where we only have a AR1 process. So when I'm looking at a AR1 process, I can rewrite my AR1 process as one minus alpha b times xt minus u, which is just equal to et, right? This can be my AR1 process. And my condition for AR1 process was that my alpha should be of the value less than 1. So for this thing to be stationary, I required that this should be less than 1. And now what we have for, so I can rewrite this as 1 minus alpha times z, and this will be the characteristic polynomial for my AR1 process. Okay. So now I know that for my ARP process, the characteristic polynomial is just 1 minus alpha z minus alpha 1, 2 till alpha p z raised to p. Right? This is the characteristic polynomial that I am looking at now. So remember the factorization that I did for the case. So maybe let's say, so we had x squared plus 5x plus 6 equal to 0. I can always rewrite this expression as x plus 3 and x minus 2 multiplied to each other equated to 0. So that I get my value for x is minus 3 and x is minus 2, which satisfy this equation right there, right? So the similar kind of a thing I will do for this equation right here. So what I will do is I will rewrite this expression as 1 minus, let me take as gz 1 minus gz square 1 minus gz cube, and oh sorry, you won't have these cubes, and squares over there. So you will only have gz, again some gz. So this will be g1, g2, g3. So when I'm writing this as 1 minus g1z, this just means that it is one of these. And I'm equating this, and this will go on till p. So 1 minus gpz. And this has to be equal to 0 because I'm figuring out the roots of this expression, roots of this characteristic polynomial which I have. Okay, and now what I do is I compare this to that. So I know that my G1, G2, G3, all of these should be less than 1. So intuitively, if I see all of these G's should be less than 1, where G takes values from 1 to P. So now what I do is, instead of writing these as G, I write this as 1 minus Z upon Z1. 1 minus Z upon Z2. And so on till 1 minus Z upon ZP. Okay. So now if I know that all of my G's are just 1 upon Z's, so my GG is nothing but 1 upon ZJ. And this has to be less than 1. So I know for this thing to be less than 1, this is just equivalent to saying that my ZJs should be greater than 1, right? And what are my ZJs? These are the roots of the polynomial that I am looking at. Does this make sense?
What are those G terms and how did we get arrive to Z upon Z1, Z upon Z2, etc.?
Okay, so you can actually ignore these G terms. These are just there to compare this GJ with ZJ. So what I wanted to do is, I just wanted to, so let us say you have some quadratic expression. We'll write a quadratic expression which is just, we won't write numbers. So AZ square plus BZ plus C. Let's say this is the quadratic equation that we have at hand. Then we can always find some factors, and these D and E's, I don't know, these are just unknown numbers to me. And I have F minus GZ, which is equal to 0 here, right? Because this is what I'm trying to equate to 0. So I started off with this and I factorized this thing, this expression into this D minus EZ and F minus GZ. So that if I multiply this, so I know that my D times F is going to be C and my E times G is going to be A, and because that is what will be the coefficient of Z square and the constant respectively, right? So that is how you get these some unknown numbers that you have. And what you do is, at the end, you divide all of this expression by D. So if you divide this by D, what you get here is 1 minus E upon D, and Z will still be there, and here you will get upon D. No, sorry. So if you just divide both the equations by D, what will you get is, so here if you divide this by D, and here if you divide this by D, here it's going to be 0 again, but here what you will get is 1 minus E upon D times Z, and here it will just be F minus GZ. And then you again divide this by F, so you get this 1 here. So to get this 1, you have this some constant here, right, E upon D, which for now I am denoting as 1 upon Z1. So my Z1 in this respect will be D upon E. Does this make sense?
Yes, ma'am.
Okay, so that is just how this is derived, and you need not also know this like by heart, but just know the intuition of why is this happening the way it is. So this is just a similar way to rewrite this. So maybe I can write that, this is something like 1 upon Z1. So instead of having E upon D and all of this stuff, what I'm writing is 1 upon Z1, 1 upon Z2. Okay. So once I rewrite this, everything as this, I know that my coefficients should be less than 1. And so this is not the exact way to do it, but this is just the intuition that I'm providing you guys to figure out why the characteristic polynomial's roots have to be greater than 1. So if you try to use the softwares, what you will get is you will have a unit circle. So whenever you try to factorize a polynomial, you get some real roots and you get some complex roots. So for here, we are ignoring the complex roots and we only take those polynomials into consideration where you only have real roots. So these roots have to lie outside the circle. There will be a unit circle and that will be the value of z's. So what you will generally have is, let's say z1 here and z2 here. And this is the value -1 and this is 1, this is 1, this is 1. So there will be a circle drawn here. And your roots should always lie outside. If any one of the roots lies inside the circle or on the circle, then this process is not a stationary process. And that is how you know, based on these roots, what the process is. But I think when you will try to do this in the R, it will become even more clearer and visual. You will get a nice picture of what it actually means to have a characteristic root which is greater than 1. So we'll leave that to it. And so let us now try to solve some examples. So while solving, we'll stumble upon difference equations. So if you have never heard of that before, don't worry, we'll do that together. So let us look at some example. So what I'm saying is that, so sometimes the roots are denoted by lambda, sometimes the roots are denoted by z, so it shouldn't be that much of a bother. But let us say I have one root which is already defined for me, and that root is 2. For the characteristic equation of the process, which is something like this. So xn minus 1 minus xn minus 2 minus xn minus 3 plus en. Okay, so also sometimes this is a very easy mistake that many students might do. So generally when we are used to writing T in the classroom or in the lectures or from any book or the questions that you practice, you have to be mindful of the terms that are being used in the question paper. So sometimes they may use n. So you have to write xn here everywhere. And what happens is you are used to writing et, so you write et instead of en. So be careful, and also the z can sometimes be written as lambda, but that's it for this purposes. We're just going to use z. So the question is, find the other roots. So this is one root of the equation that we already have, and they're asking us to find the other roots. So first question, how many roots do you think this process's characteristic polynomial should have? How many roots should there be? Okay, so I think it's easier if we just first write the characteristic equation. So I can rewrite this as xn minus 11 upon 6 xn minus 1 plus xn minus 2 plus 1 upon 6 xn minus 3 equal to en, right? And now I will take this all of these x's common. So I'll just write a xn here and I'll write 1 here minus 11 upon 6 xn minus 1 plus b square plus 1 upon 6 b cube, and this is just equal to en. Does this make sense? So
Yes.
now this right here is my characteristic polynomial for this process. So how many roots do you think this polynomial should have?
3.
3, right? Correct. Very good. So we already know one of the roots. So what should I do to figure out my other two roots? And remember, this characteristic polynomial is generally written as phi, which is a function of z. So here
Now
I'll have this one.
we should divide it by b minus 2.
Yeah, we should divide it, right? So what I'll have is plus z square plus 1 upon 6 z cube. So always, try to avoid working with b, because we know that b here represents the backwards shift operator. So just substitute it with z, which is some variable, and then try to work out with that. So let us now try to divide this
Yes,
expression.
ma'am, but I have a question. How can we convert b into z? Matlab, how does this, how is, how does it even form an equation if b is the back, backward shift operator?
Okay, so remember when I discussed the backward shift operator in the previous lecture, I used to write b square and then we had this difference operator which was equal to 1 minus b. So I also had, wait, let me maybe go back to that. Okay, so what I did was I have this difference operator here and I wrote this as 1 minus b, right? But when I try to figure out its square, I wrote it as 1 minus b square, and I was just using this backward shift operator, but still I could use the general expansion that I always do for 1 minus b square,
Yes,
right? As if b were just a random variable.
yes.
So even if it is a backward shift operator, we can still, use these expressions. So it doesn't matter. But
Yes,
just
ma'am, but
here,
the values we'll get for z are the values we'll get for b.
yep,
But
yeah.
how can b take any value since it's an operator?
How can be exactly. And that is the reason why you write these Zs.
No, at the first place only, how can we equate b with z? How can we consider it equivalent?
Okay, so let us say if I don't equate it to Z and I'm still working with B, so at the end I will figure out some values for B, right? I'll have some values for my B,
Yes, and I
right?
think b can't take any value since it's an operator.
Exactly. And we know that even though B is an operator, it can still, be operated on as if it were just a random variable. If I have 1 minus b square, I can use the same formula that I would have used if I were having 1 minus z squared,
Yes,
right?
ma'am.
So what I do is I just use this z as a proxy for my b.
Just to solve the equation.
Yeah, just to solve the equation.
Okay.
I mean, I know this is a bit weird. This is weird for me as well. But yeah, this is just, yeah, it doesn't change the results that you have. And these are just, some tricks that you have to use when you're dealing with math
Yes, ma'am.
to make sense of whatever you have. But that was a really good question. Okay, so Now we're solving this question, and now what should we do is we should divide this. So we have this one here, and we are trying to figure out some three expressions, right? So one we already know is z minus 2, and we have to figure out this a and this b, which will equate this to 0. So what I do is I divide this expression with this. So I know that I'll get this, because if this 3 when multiplied together give me this expression, so if I divide this by this, it should give me the rest of it. So what I do is I write this in decreasing order of z's power. So what I will have is 1 upon 6 z cube plus z square plus z square minus 11 upon 6 z plus 1. And now I'm dividing this with z minus 2. So now if you have to perform this long division, I hope each one of you already knows how to perform this long division, but still I just go to this process, but a bit faster. So what we will have here is, okay, I think I just wrote the question wrong. So I'm not changing much, but just these. Okay, so what we have is minus 1 upon 6 z cube. So if I were to have this and I want to remove this term, what I'll do is I'll write minus 1 upon 6 z square. So that if I multiply this with that, what I get is minus 1 upon 6 z cube. And I also have this 2. So I'll have to write it as minus 2 times minus 1 upon 6. So it will just be plus 1 over 3 z square. And this will get cancelled out. And 1 plus 1 upon 3 is what? So remember, when I'm trying to do this thing, it's very important to remember that I'm subtracting this whole. So this minus will become plus, and this plus will become minus. So now what I will have here is 1 minus 1 upon 3. So 1 minus 1 upon 3 is just 2 upon 3 z square minus 11 upon 6 z plus 1. So this will come down as it is. Okay. So the next term that I will have is z. So I will divide this by z, and what I get is 2 by 3 z. So I'll again have this here z square, and minus 2 multiplied with this, I will get minus 4 upon 3 z. And again I'll do this. So this plus will become minus, and this minus will become plus, and this will cancel each other out, and I will have 4 by 3 z minus 11 upon 6 z, which gives me minus a half z plus 1, which is carried down as it is. So now I will have to multiply this z with minus a half. So I'll have minus half here and minus half z. And again, this will get multiplied with that, and I will have plus 1. And this cancels each other out, right? If I have minus here and minus there. So this will become plus. Does this make sense?
I'm right.
So now I know that the expression that I'm looking for here is just that. And this right here is the thing that I have there. Okay, so now I can use the factorization method or just the quadratic formula method to substitute in the values of A, B, and C to figure out my other roots right? I don't have to do this division and everything again. So let us continue with this. So now I know that I have z minus 2 here, and here I have this term, which is minus 1 upon 6 z square plus 2 upon 3 z minus 1 upon 2. And again, remember that to figure out the roots, we're equating this to 0. So what you can do is just multiply everywhere by 6. So you multiply here by 6, you get 0. And if you multiply here by 6, you leave this bracket as it is, and what you get, so let us just multiply by minus 6, so that we get a 1 here. So you have z square, and if you multiply here by minus 6, what you will have is minus 2. So this will become minus 4z. And if you multiply by minus 6 here, you will have plus 3, right? And now it's easy to see the equations that will satisfy this. I have 3 and I have minus 4. So what I will have is so what I will have is z minus 3 and z minus 1. Does this make sense? So now I know that my roots are 1, 2, and 3. So is this process stationary? Remember what was the condition for my ARP process to be a stationary process? That the roots of all the that all the roots of my characteristic polynomial should be less than 1 or greater than 1?
Less than.
Less than. Okay. What about others? What do you guys think?
Greater than 1.
Greater than 1? Okay, so let us have a look at what we studied. So remember, when I was looking at a AR1 process, okay, maybe I should discuss that. So what we did was, we had our ARP process and we had our characteristic polynomial, and the roots were Z1, Z2, Zp, which I could write as this. And I know that all of these individual z's, so all of these roots have to be in absolute terms greater than 1. So let me see what happens with AR1. I know that my alpha should be less than 1, right? So if I'm looking at the root of this expression, what I have is 1 minus alpha z equal to 0. So I can rearrange this and I'll get z as 1 upon alpha. So I know that my alpha is less than 1. And if alpha is less than 1 and the numerator is 1, I know that my z is automatically greater than 1, right? So the value of my z there is greater than 1, which is again the root of this polynomial function. So what I do is, I want the value of my z's here to be greater than 1 always, and it cannot be equal to 1. So I have this 1 here, and whenever the root is equal to 1, you call it as unit root. And we'll have a look at, there's something again that you can do if you have a unit root. And there are some econometric tests. I think if you must have studied statistics, the unit root test. And that is just some another thing that comes from this time series chapter. So here we know that because we have this root here, which is less than or equal to 1, I know that this process is not a stationary process. Does this make sense?
Yeah.
Does anyone have any doubts? We'll try to solve another question again of this ARP process. So I'll give you guys some 2 minutes to think about this and let me know if you have any doubts. Try to go through, the starting of the sum what we did and what were the conditions we had. Okay, let me just continue. Does anyone have any doubts?
No.
Okay, so let us try to solve another question. So this was just to, make it clear how should you work with the characteristic roots and you want them to be greater than 1. So there will be confusion with, things which should be greater than 1 or less than 1. And now you are only studying AR. And when you study MA, there will again be some other conditions which will be in tandem with the AR one, not very different. But yeah, we'll have a look at that tomorrow. So let us say now again, we are looking at another example. So I have a AR2 process now. I have a AR2 process. So I'll have xt equal to 5 upon 6 xt minus 1 minus 1 upon 6 xt minus 2 plus et. And the question is to find the autocorrelations for lags 0, 1 and 2. So if I want to figure out the autocorrelation, what should be my first step? Anyone? So remember, I'm talking about autocorrelation, not partial autocorrelation. So for autocorrelation, the formula is similar to the correlation, but just with the variable itself, right?
Variance.
Variance upon, yeah, exactly right. So variance is gamma naught. And if I want to figure out my rho 0, what will it be?
Alpha.
Gamma 0.
That's it.
It will be 1.
It will be 1, right? Because my autocorrelation is nothing but covariance upon the variance, right? The simple formula that I always have for correlation is what? Covariance upon the square root of variance of one guy and the variance of another guy. And over here, the variances are the same. So variance squared under root is just the covariance upon the variance. And covariance will be, because here we are looking at lag 0, the covariance will be from with xt to itself, and the variance is gamma 0. So gamma 0 upon gamma 0 will be what? 1. So I know that my rho 0 is always going to be 1, irrespective of any process that I'm looking at. Any AR process that I'm looking at, my rho 0 is going to be 1, right? Okay, so now what I should do is, I should maybe figure out what happens with lag 1. So let us just write the formula, that the equation that I would use. So let's say I have xt comma xt, and this is for gamma 0 that I did. So I'll have covariance of xt with xt itself. And what will be the value that I have? So let us rewrite this xt as this. So I'll have 5 upon 6 xt minus 1 minus 1 upon 6 xt minus 2 plus 80 comma xt. And I can again rewrite this as 5 upon 6 covariance of xt minus 1 comma xt minus 1 upon 6 covariance of xt minus 2 comma xt plus covariance of 80 comma xt, right? And I can again rewrite this as 5 upon 6. So what I have is covariance of xt minus 1 comma xt. And I can see that this is nothing but just gamma 1, right? And if I have to write this will be what? Gamma, what will be the subscript here?
2.
2. So this will be gamma 2. And this will be what?
0.
Any other guesses? Does everyone agree that it should be 0?
Yes.
Okay, and what about others?
Yes, ma'am.
Okay, good. This is nice. So let's say I try to write this covariance of 80 and I again expand this xt that I have. So what I will get is 5 upon 6 xt minus 1 minus 1 upon 6 xt minus 2 plus 80. And now if I ask you guys what will be the answer for this, will it again be 0?
It will be variance of ET, that is 1 or 6.
Right? What I will have is covariance of ET, and this won't be related, but this ET will be related, and that is just sigma square. Okay, so whenever you're working with time series, you have to keep this in mind. Even though superficially, some of these variables might not seem to be related, but they are, because if you expand this xt, you know that you get this et term in its expansion, right? So you will have this et correlated with et, and the covariance will not be indeed 0. So it will take some value which is sigma square. So I can just rewrite my gamma 0 as 5 upon 6 gamma 1 minus 1 upon 6 gamma 2 plus sigma square. So this is one expression that I have. Now I try to use covariance of xt comma xt plus 1. And what will this be? Gamma 1, right? And now what I do is I rewrite this expression. So I have covariance of xt comma. And now if I substitute for xt plus 1 here, what will I get? I will have 5 upon 6 xt. So I will have 5 upon 6. Just a minute, guys. Okay, so what you will have here is 5 upon 6 x t, because now instead of t, I have t plus 1, and here I will have minus 1 upon 6 x t. What will I have? Anyone?
T minus 1.
T minus 1, right?
Yes.
So I'm just adding 1 over everywhere, so, and this will be e t plus 1. So now if I were to rewrite this expression like this using gammas, what will this be? So first I'll have covariance of xt with 5 upon 6 xt. What should I write here?
5 upon 6 covariance xt comma xt. That is
And that will be
gamma naught.
gamma naught, right? So this is just gamma naught. Okay, and for the next term, what should it be?
Minus 1 by 6 covariance xt comma xt minus 1.
And that will be?
Gamma 1.
Right, that will just be gamma 1. And the other thing will just be 0. So now you have this expression. So this is my second expression. And let's say if I try to, simplify this expression. So I have gamma 1 here and I again have gamma 1 here. So I can maybe try to do something. Try to add and subtract 1 upon 6 gamma 1 from everywhere. So I can just take this here. So I'll have 1 plus 1 upon 6 gamma 1 equal to 5 upon 6 gamma 0, which will give me what?
7 times gamma 1 is equal to 5 times gamma naught.
Right. So if I were to rewrite gamma 1 in terms of gamma naught, what I will have is 5 upon 7 gamma naught. Okay. Now let us figure out the covariance of xt with xt plus 2. Can anyone dictate what this should be like? So I'll have covariance of xt, comma, 5 upon 6 x t plus 1 minus 1 upon 6 xt plus e t plus 2, right? So what should be the value for this?
5 by 6 gamma 1
Yes, and
minus 1 by 6 gamma naught.
yep, and 0 again, right? So I again have this expression right here. And what I can do is, I can substitute this value of gamma 1 here to figure out gamma 2 in the terms of gamma 0. So let us do that. So I have gamma 2 equal to this whole term there. Set. Okay. Yeah. So I have my gamma 2 as 5 upon 6 and I had gamma 1 here. And I know I can rewrite my gamma 1 as 5 upon 7 gamma 0 and this will just be 1 minus 6 gamma 0. So if I were to solve this expression, what will I get? Anyone want to try to solve this? So if you
18
solve
plus
it, you will get gamma 2
18.
as 3 upon 7 gamma 0. That is the final answer that you will get. So I would encourage you all to try that on your own now. Okay. So now I know what my gamma 1 is in terms of gamma 0 and what my gamma 2 is in terms of gamma 0. So remember the expression that I had in the beginning, this. Now I will substitute gamma 1 and gamma 2 in this expression. So what do we get? So what will we have is gamma 0 being equal to 5 upon 6. So now I will have gamma 1, which is 5 upon 7 gamma 0 minus 1 upon 6 gamma 2, which is 3 upon 7 gamma 0 plus sigma square. And if you go on to solve this and rearrange all of these values, what you will get is sigma square in terms of gamma 0. So you will have 1 minus 25 upon 42 plus 3 upon 42, which will be nothing but sigma square is gamma 0 times 0.47619. And if you again rearrange this, you will have gamma 0's value as 2.1 sigma square. And this is what you were looking at, right? So now you have a definite value for gamma 0. Now if you can easily figure out using the equations of gamma 1 and gamma 2 in terms of gamma 0, the values for gamma 1 and gamma 2. So I substitute this gamma 0 in there and I will get for gamma 1 1.5 sigma square. And for gamma 2, I'll have 0.9 sigma square. So you all should verify this answers on your own. Okay. But remember, we were asked to figure out the autocorrelation, not the autocovariance. And we know that the formula for autocorrelation is nothing but, so if I have gamma k, it is, if I have rho k, it is gamma k upon gamma 0. So I know that my rho 0 is just 1. And if I were to figure out my rho 1, it will be gamma 1 upon gamma 0. So my gamma 1 is 1.5 sigma square and my gamma 0 is 2.1 sigma square, which will give me my value for rho 1. And that will be something like 5 upon 7. And if I were to figure out my rho 2, that will be gamma 2 upon gamma 0. And that will just be 0.9 sigma square upon 2.1 sigma square, which is nothing but 3 upon 7. Does this make sense? So remember, we were asked to figure out the values for autocorrelations for lag 0, 1 and 2. So what we did was we figured out the value for covariances. And for that, we know that we have to figure out the value for gamma 1, gamma 2 and gamma 0. So these are the 3 variables that we have. So we need 3 equations in 3 variables to solve, to come up with the values. And we used the fact that these xt, xt plus 1, and you can also use covariance of xt minus 1, xt. And I think that is how they have solved in your book. But I deliberately solved using xt plus 1 just to show that you can do it anyways. And you figure out these 3 equations. So this was the first equation, this was the second equation, and this was the third equation. And then you simultaneously solve. So instead of just looking at all of these 3 equations at once, what helps us is to look at 2 equations first. And generally, like this equation was very simple, but generally you might have some, let's say this was not only AR2 but AR3 process. So you will have some gamma 2 here as well. So you first look at this equation and that equation, and you try to eliminate one of these variables. And then you will have left is just these 2 variables. And then you can easily get a relationship between those. And then you can again substitute one of them here. And I guess I need not tell you guys how to solve simultaneous equations. So you solve those equations and you get the values of each of these in terms of gamma 0. And then you substitute these values in gamma 0 to figure out the relationship between sigma square and gamma 0. So we know that sigma square is just a constant, and now we have the value for gamma 0. So again, substituting this back in there, we got the values for gamma 1 and gamma 2. And now that we know this gamma 1, gamma 2, as well as gamma 0, we can easily figure out the autocorrelation values for each of these lines. Is that clear? And again, if you want to figure out the partial autocorrelation, you can just use the formula from the page number 40 of your table booklet and substitute these row 1, row 2 values to get the values for your partial autocorrelation. Is that clear?
Yes, ma'am.
So I think that is all that we are going to do today. We'll continue this session tomorrow. And again, tomorrow I'll take a lecture from 7 to 9. And I think it might go up until 9:30. I'm not quite sure about that. But yeah. Do you guys mind if I take a lecture from 7 to 9:30 tomorrow? Or is it too
No.
much?